Okay.
We are happy to welcome Tannen on provenance analysis for first-order model checking.
Right. Thank you very much, Kevin. So this is work done jointly with Erich Grädel, who is a professor at Aachen University. And there are several ingredients here that are coming together, perhaps unexpectedly for some of the audience. One ingredient is provenance. The other one is first order, which means that we're going to look at the language of first order logic. And the third one is model checking. And here I did not obviously put it in the title, but obviously the kind of model checking that we are interested in is finite model checking. That is, this is a work that was inspired by the same problem in the context of databases, and a database can be seen as a finite model for first-order logic, except that it doesn't have functions, just relations. The tables are the relations of the model. And I'll begin by explaining what my notation is. So as you can see here, how does this go? No, doesn't matter. As you can see here, we will have a model, and that's the Gothic A, the A there, and a sentence, and we are interested in understanding the question, does this sentence phi hold in that model A in more depth? Now, in logic, one is only interested in whether the does hold or does not hold. And because this is inspired by work in databases, we're going to ask a set of more interesting questions about this, which turned out also to have corresponding interesting interpretations, even for pure logicians. Well, one hopes. Okay, so consider that, as I said, a finite model. And I can think of this finite model as a structured collection of information items, data. And you'd like, as I said, to know more about this sentence being true in the model. For example, I might be interested in the cost of this truth. Now, how can that come about? Well, that can come about in certain applications where, in fact, verification depends on data, the price of data, data pricing. And other applications, you might be interested in how much confidence should you have in the fact that the sentence holds in the model. And yet another set of applications that's more simpler to understand here, you might want to know, okay, it's true, but if you think of what we're going to define precisely what it means to have a witness for that truth, a witness for that model checking, how many different witnesses does it have? So these are all interesting questions. I'm not going to talk about it at all, but there is a fascinating connection between model checking and game theory. So there are the so-called model checking games, and there are actually relationships also with those games and with strategies for winning those games. But in the papers that we wrote based on this is sort of the first work we did. We do have the development also for games. Now, how does one answer the question, what is the confidence you should have? Of course, you have to have some a priori confidence in the data in the model. That is, if you believe in the model data, then you believe in the truth of the sentence, but the confidence you would like to call how much you believe it. That is, you would like to put some numbers on that, and we shall see that this is possible. Okay, so I'd like to avoid this, not to have to. Do you know No?
Best way might be to change the sleep setting on your device. Would you?
You think that's what's happening?
It seems to be going to sleep doesn't hallucination.
Yeah. All right. I'll just try to deal with it, because that takes time. Okay. So notice that some of the questions that we might ask are not Boolean questions like true or false. They are quantitative. And for those of you who have contemplated methods like Boolean grounding for answering such questions, you will realize that they will not work for things like confidence or number of witnesses or something like that. Now, this, it turns out, can be done in a unified framework, and we know that because we have developed such a framework in the context of database languages. And now I'm developing it here for first-order logic, which is more general than database languages. And this framework is based on asking a priori what we call a provenance question, and then using the answer to the provenance question, we specialize that answer for instance, confidence or cost, as we will see. So here is an example. Here are examples of provenance questions. Which of the information items in the model are actually used in checking the sentence? Because maybe not all of them. So it would be kind of boring if all of them are used. But this is not such a difficult question. A more subtle question is if you ask, well, in terms of that information, why is phi true? That is, the why here is a substitute for the possibility of having alternative reasons. There may not just be one way in which we actually can check that sentence. And if there are multiple ways, do we have a way of talking about those? And this is not such a good, so just expressing everything in terms of which, why, and how is not great. In particular, the how is just meant here to be what is the most I can say about the process of model checking? How can I analyze that process of model checking? And the work that we have done in the context of languages for databases has shown us that you can do this with using a framework that uses the structures of commutative semirings, and I will explain why. What these commutative semirings are a generalization of the Booleans. So the Booleans, namely the set true-false, do form a commutative semiring, namely the plus and times. Well, they form a lot more than that. They form a Boolean algebra, but the plus and times are the or and and. Okay?
Or is inclusive, not exclusive?
Yeah, it's inclusive or. Yeah. So the exclusive or, of course, you have what's called the Boolean ring. Okay. So that actually will take us to a non-standard semantics for the full idea of logical truth to first-order logic that, since this work was started about 6, 7 years ago, was explored in some depth especially by Erich Grädel with his students in Aachen. So just to fix the terminology, what do I mean by a commutative semiring? A semiring interprets plus as has plus as the additive monoid, and times as the multiplicative monoid. And for us, the plus and times correspond intuitively to the following notions about the use of information. Plus interprets alternative uses of information. That is, if you say that you have provenance P plus Q, that means that P and P is some way of talking about the one provenance. For example, a source where the information comes from, and Q is another source, then P plus Q means that same information came both from P and from Q, and you want to record that. On the other hand, times is interpreted as joint use of information. For instance, you build a pair, and one of the components come from some source, and the other from another source, so use multiplication. So what are the examples of commutative semiring that we use? The Booleans I've just told you about. So this is, where we do logical truth. For us, however, when we work in a general commutative semiring, only the intuitive interpretation of 0 is the obvious one. You can guess it's going to mean false. So false is definitive. So the question is, what is, if you interpret the first of the sentence in a commutative semiring and you get something that's not 0, what does it mean? Well, it means that it's true, but there are a variety of values, kind of shades of truth, that can be associated with how that sentence is true in the model. So a nuanced interpretation for true assertions, shades of truth. Now, other examples. The natural numbers, with just plus and times, they form a commutative semiring. It can be used, and in the context of this interpretation here, the work here, to count witnesses or proof trees. I'll explain what those are. Then you have an interesting semiring called the tropical semiring. How many of you have heard this bizarre name? Yes. Do you know why it's called a tropical semiring? So because the work was in early years promoted mostly by Imre Shimon in Brazil. Huh? Yeah, at your university. And he was probably very happy, but did not ask for anything. But French researchers working on the same topic said, oh, we need a name for this semiring. And since Imre was from Brazil, they called it tropical, although frankly, I would have called it equatorial.
It's subtropical where he was, I think.
I mean,
so I don't even know if
the equator crosses Brazil.
Just shaves off like the top of it.
Okay. All right. Let's not waste too much time on this stupid topic. It's a fascinating name, right? So here you see in this semiring, times is plus, which leads you to a whole bunch of strange things. But what we can do is use this one for doing what I proposed at the beginning. Let's assign cost to using data. Then there is another semiring that's kind of easier to interpret. The values between 0 and 1, and plus is max, and multiplication is multiplication. This is called a Viterbi semiring. This one can be used, you're going to say, oh, probabilities? No, unfortunately. But confidence scores. Why not probability? Because max is not really what corresponds to, sum of disjoint events or anything like that. One thing to observe, the tropical semiring and the Viterbi semiring are actually isomorphic. I personally like to think in terms of the Viterbi semiring. It's a little easier. Here is another semiring that is also interesting. Suppose that you have these 5 values, P, C, S, T, and the 5th value is 0. I'll explain. Now, you can make this into a semiring because if you assume a total order, you assume the total order P is less than C, less than S, less than T, because I'm going to interpret P as level of access to information. So P is public, C is confidential, S is secret, T is top secret. And I need 0 to make this into a semiring. So, the best thing I can say about 0 is that it's even more than top secret. So it's so secret that nobody can see it. That's the interpretation. And in fact, it's, what you have here is you have a total order, but more importantly, this forms a distributive lattice. And actually, any distributive lattice, even not totally ordered, could be used for the purposes of assigning levels of access. Here's another one that maybe some of you have been fascinated. Like in my youth, there were a lot of people who were doing fuzzy mathematics. But you know, I didn't catch the bug, because if I was just taking everything that we knew in math and just making it fuzzy, and the depth of the theorems was not that dramatic. So the fuzzy semiring is just 0, 1 with max and min. But for the purposes of provenance, the most important example of semiring is that of polynomials, because it turns out that, of course, this is the free commutative semiring generated by the set of x, which are indeterminates. And these we're going to call provenance tokens, the elements of x, and the polynomials have also acquired the name provenance polynomials. So when people talk about provenance polynomials in certain circles, very certain circles, they mean these polynomials. Notice that the coefficients are not integers but natural numbers. Dana?
What's the difference between x and 2x?
So 2 as in coefficient? 2 little x, or? Because there is an x which is the set of indeterminates.
Oh, that's all the indeterminates. Yeah.
So the
Take
x is the...
Yeah.
Pardon me?
Take one of them, a and 2a. Okay.
Yeah, so 2a is a plus a.
I know.
Of course you do. But I don't... What are you...
In terms of provenance. Does it mean it has a provenance?
Ah, yes. Thank you. See, I lack enough imagination to figure out. So 2a means that there are actually 2 different ways to justify something, but both ways use a piece of information in the input that is the same, a. I could also label different pieces of information in the input with the same token, because maybe they come from the same source. So then the answer would be, oh, there are 2 ways to justify this answer, alternative ways to justify this answer, and both depend on data coming from source A. Okay, so you have, you know, the usual property for the freely generated semiring. So this was the one that we used for a general form of provenance for positive relational queries. We even extended it later to data log, actually in the same paper, but there we had to use not polynomials, but we had to use, because we wanted the least fixed point, in the end we had to use power series. Now, what was not quite all right with that previous approach was we didn't know how to deal with negation, not properly. And it was in particular all these beautiful properties of negation that, you know, there's the duality that we all love and, you know, use. We're not at all clear how to deal with them. Various proposals were made. One of them was to use something called monus for the relational difference. And, you know, I've been talking to Dana about monoids with monus, and he's helping me understand a bunch of things. But the approach that Erich and I took here is quite different. And we seem to be kind of confident that this is going to give you a lot of insight that was not obvious with other approaches. So for the rest of the talk, I'm going to use an example and explain. I mentioned the word witness several times, and explain what I mean by that. Then I'm going to define what does it mean to have first-order finite model checking interpreted in an arbitrary commutative semiring. So this is like a semantics for logic, but not in the Booleans, but in an arbitrary commutative semiring. And then we will introduce a special semiring that plays the same role as the polynomials I just mentioned before, but these are going to be called dual indeterminate polynomials, and they work well with negation. They play well with negation. And well, then I most likely run out of time and have to skip this, but I will talk about applications of this provenance on all kinds of questions having to do with provenance analysis, with reverse provenance analysis, with using provenance to answer questions like, but administrator, why isn't this tuple in the answer to my query? I thought it should be. It's like, you know, this happens all the time. And the administrator, I have no idea. Or even worse, why is the answer to my query empty? I knew there was some information that should have come out there. Right. So questions like that. All right, so I just mentioned that. So some of the work that I did at the end, actually I did with 2 undergrads and a postdoc at Penn after working with Erich. So here is the running example. My model is going to be, as usual in finite model theory, a digraph. I'm going to denote by E the edge relation. And I'm going to say that a vertex in the digraph is dominant if for any other vertex, distinct vertex, there is an edge from from the dominant one into the other vertex, and there is no edge going from the other vertex into the dominant one. So imagine that dominant vertices are like the centers of stars. They have arrows to everybody else, but nobody else has arrows to them. Okay, this is not a deep concept in graph theory, but that was not my point.
I don't understand your formula there, I'm sorry. Can you read it again?
So X is dominant.
Yeah.
The vertex X is dominant. If for any vertex Y different from X,
Yeah.
you have an edge from X to Y, and you have no edge from Y to X.
Oh,
Okay. And then you can quantify that and look, for example, at the sentence, there is no dominant vertex, which is a sentence, so it's not a query, as it were. You all know what it means to put the first order sentence in negation normal form. You can push the negation all the way to the atoms. And I will need things like that. So here is what this one looks in negation normal form. And here is a first example of a model in which I can talk about this digraph. It has vertices A, B, C, and the edges that you see. Are the heads of the arrows visible? Okay. And this is what I mean by a witness. So right there, and I beg you not to try to decipher what's in that tree, but right there is verification that this graph has no dominant vertex. Okay. So the verification is uses 2 observations. I can talk about such verifications as trees because this is a finite model. So the quantifiers can be, for example, the painful for all quantifier can be verified with a rule in which the premises are for every element in the model. Okay? And the existential quantifier, you can just choose one vertex for which what you want works. Disjunction again. So the things you would expect. And on as usual, this tree has the root, no, as unusual, this tree has the root down, just like biologists want, and the leaves up. And what you have on the leaves are the atomic facts of this model. Things like, yes, there is an edge from B to A. No, there is no edge from B to C. Yeah? So that's what I mean by witnesses.
Some of the leaves in big boxes and big letters and
Why? so that you do not read the other ones, because we would spend an hour you asking me what to justify. Why is it?
It's just a selection of different ones that show up.
Yes, so this, and it bolsters the point I had before. This sentence can be verified with only some of the information in the model. So for example, I need the edge from B to A, that there is an edge from B to A, to justify that A is not dominant. And I need the absence of an edge from B to C to justify that B is not dominant. And this one should have been big, but you know, I didn't want to mesmerize you with my graphics. Okay? All right. So let's move on. In this context, I'm going to give semantics. I will even use the good old semantics brackets, which were perhaps introduced by you, Dana, the double brackets. Can we accuse you of that?
They had an evolution. First, I used double things, but then it was better to use pointed ones, so no beginning from end.
Okay. So here is our semantics for first order logic in this, for truth in a model. But the big difference is the semantic values are not going to be true or false. They are going to be elements of a semiring. Another thing that I should probably will have to repeat later on is that this whole approach relies on what's called the closed world assumption, which means the following. Because we are talking about both what's true in the model, and that's usually visible in the picture of the graph, but this is first order logic, we also implicitly assume that if an edge is not in the picture I give you, then that's the fact that's not there. Okay? So that's called the world universe. So I'm not assuming the possibility of things that we don't see. We just start with a finite set of values. In the case of the example I just showed you, they are the vertices of that graph. So you start with a finite set of ground values, and that's the universe of the model. And we have facts and we have negative facts. These are the usual atomic literals. And I'm going to denote lit of A, the facts, or together with the negated facts. And in order to define the semantics, I need to start with an interpretation for these facts. So, and the negated facts. So a K interpretation is a mapping from the literals to K. Now, at this such that, which we will now extend to first order logic. At this point, usually people are up in arms against me because I am assuming any possible interpretation. How can that be, right? So I'm assuming any function, but I can start. Not all of them are going to be nice and well behaved, and I will later have to work with interpretations that make sense for what I need to do. But I don't see why I should not show you the definition in its most general form. You can define it for any kind of mapping from the literals. Okay? So this is a definition. For the atomic formulas, you use the interpretation that's pre-given. So this is exactly a variant of what you do, you know, for Tarskian truth in a first order model. So for equality or any operation, I actually, for the moment, choose to interpret those as 1 if the equality holds, and 0 otherwise. I'll explain why, because I have a certain meaning for 1 and 0, which of course in the case of Booleans is the right one. Okay? And it's a question, why do I not interpret equality or this predicate, this inequality, in a more nuanced way? But for various reasons, we skipped that. Okay, So now, you're not surprised to see that conjunction is interpreted as the multiplication of the semiring right there. Yes? And disjunction is interpreted as the addition of the semiring. David?
If I think in terms of tables, I think in terms of rows, is it that every row has an element of k?
So the answer is yes. So the interpretation labels every fact with an element of k. From the perspective of databases, the positive facts, the ones that are in the database, are indeed the rows of the table, and each one of them, you can think of each one of them as annotated by an element from the semiring. But we also have this table of not, imagine, which you don't bother to write it down.
We have we have the Lex Luthor, or
the anti-relation, which
also
you also potentially want to label with some element in the semiring. Okay, so the quantifiers are also summation and product, and that's because we have only finitely many elements in this finite model. And finally, the innovation that Erich came up with, because I told him I don't know how to deal with negation, he said, wow, why don't you use negation normal form? Okay, so a priori I was very skeptical, but things worked so nicely after that that we just got a lot of mileage out of that. So the idea is the following. If you want to interpret the negation of phi, what you do is you put that negation in negation normal form. Now, the negation normal form doesn't have negation at the top now. It has it all the way to the bottom, so you can apply the other rules, recurse on the other rules for the definition until you get to the bottom. And in fact, doing that is actually very natural, because you could even put a negation, you can even put the sentence in negation normal form to begin with, and you do get the same interpretation. You get the same element of the semiring. Dana?
Your predicates are only one-place predicates, though?
No. The A that was R of A was bold, bold font, which because I hate those bars on top. No, they were multiplace.
Okay.
But yes, you're right. I should have worried about that. So, sanity checks. The first one that you want to have is the following. Consider the interpretation in which you have a model, and now every literal, positive or negative fact is interpreted as true when it's true in the model. Then, in that case, the sentence, when you interpret it in this semiring, in the Boolean semiring, is true. If and only if it holds in the model. Yes? Sanity check. I mean, if this doesn't hold, we're out of here. But what will perhaps surprise you a little bit, look at this different interpretation. So now I'm not working in the Boolean semiring. I'm working in the semiring of natural numbers. And I'm interpreting a literal as 1 if it's true in the model, and 0 otherwise. And now I evaluate this in the semiring of natural numbers. The result is exactly the number of proof trees that witness that. Right. So this was encouraging, so we moved on. The other thing that is very useful, and that I knew even to state, because similar theorems were developed for the relational algebra and data log and so on, is a commutation with homomorphisms. So if you have two semirings and a homomorphism, they better commute, the homomorphism commutes with the interpretation of a sentence. So if the literals are interpreted in a commutation with homomorphism way, then so are the entire sentences. So The next thing that you would like to do is develop what we develop for databases, which is a terse capturing provenance expression that could then be specialized in all those semirings and compute things like the number of witnesses, as we have seen, or confidence, or access control, or things like that. So now in order to do that and to deal properly with negation, we have done the following development. We used a set of indeterminates X to annotate the facts. Yeah, so these are the labels. So now for abstract provenance, the elements of the semiring are going to actually be special labels, just names. Think of these tokens as, for instance, where the data came from. So this tuple comes from Val's database. This tuple comes from Jose's database, okay? And so on. You have no database.
But one is very much more trustworthy than the other.
So now, I don't have a database either. So we're going to use for the negative facts a mirror image of X. We're going to call it X bar. Its elements are going to be in one-to-one correspondence with the elements of X. And, people think of this as the negation of a Boolean variable, but it doesn't have to be, and it isn't, right? So little p may be the label of a fact that appears in your database, and p bar is going to be the label of a fact that does not appear in that database, and it's a label of the negation of appearing. All right? So we call these things complementary tokens, and now you define, you take all polynomials in X and X bar, and you quotient by p times p bar is 0. Okay? So that's an ideal. So the semiring of polynomials quotiented by the ideal generated by all the p times p bars, or you can think of the least congruence generated by those, is also a semiring. And so the result is denoted n of x comma x bar. All right. We call these things dual indeterminate polynomials, and that being a mouthful, I'm just going to shorten it to dual polynomials. But I really need to say it's different from the ones that work for positive query languages. So for these polynomials are going to be interpretations for first order logic. So how am I doing on time, Kevin?
Definitely 10 more minutes. You go a little bit more than that.
All right, I would love if you let me a little bit more. This is the universality property of this construction, which is similar, but you have to assume that p and p bar are mapped to elements whose product is 0. And this is how we use it. So we call this thing a provenance tracking interpretation. So what we're going to do is use an interpretation for the model in the semiring of dual polynomials. The semiring of dual polynomials is a semiring. And I'm going to be disciplined in that whenever I am going to label a fact by a positive token, that corresponds to a fact that is true. And for negative facts, I'm going to label them with complementary tokens. Okay? But notice I use different letters, T, P, Q, R, S. So this is the interpretation, and everything that's not represented by the dotted or the solid lines will be, in fact, interpreted as 0 and 1. And the intuitive understanding of 0 and 1 is the following. 0 means that the fact is not in the model. Now, the fact could be negative, and so for example, if you have an edge from A to B, then not E of AB is actually interpreted as 0 because it's, yeah. 1 is more subtle. 1 means that the fact is true, but I choose not to track its provenance. And I use this label 1 as a neutral label that is going to propagate through all the calculations of the meaning without affecting the calculations, just saying, okay, yeah, that fact is available, whether positive or negative. Is available for free, no need to track it. So here's an example. The sentence that we saw before that says no dominant vertex, there it is, calculates in the semiring of dual polynomials to this particular polynomial. Now this one is a simple one because it has only coefficient 1. Every monomial there has coefficient 1. So by the way, when you look at things like q bar t, that's a monomial with two variables. One is q bar and the other one is t. Okay? And it's a theorem that the monomials themselves correspond to proof trees that witness that sentence. In that every letter that appears in the monomial actually is the label of a leaf in the proof tree. Okay? So, yeah, okay, there are 8 witnesses for this one.
For that particular graph?
For the one, yeah, the one I pictured. I mean, of course, if it's a different interpretation, it would be a different polynomial. Okay, and interestingly is that provenance can be used as an intermediate stage in which you calculate things abstractly, which you can then specialize by interpreting this, by evaluating this polynomial in a particular semiring. So for instance, here, let's assume that, that I have confidence 3/4, 0.75 in every positive fact that I listed there, and 0.66, 2/3 in every negative fact. There's no reason to assume related numbers. And everybody else, I have confidence 0, the ones that I'm not working with. And then you can calculate this, and the polynomial evaluates to, you see it, max and multiplication, 9/16. So whatever 9/16 is, that's the confidence that there is no dominant vertex in that model, assuming that I trust the information of the model with those confidence values. Okay, I'm going to have to skip this. Okay. So what can you do with these animals, the dual polynomial? One thing you can do, for example, is to explain missing query answers. So here is another model. It's not exactly the one that I had before. This one is meant to be a little different. And in this model, I'm going to look not at the sentence, but at the query. That is a sentence with one free variable, dominant of x. That is, x is dominant. So if you take a look at this, b is dominant here. Yeah? But a is not. So somebody who might expect A to be dominant may ask, why is A not an answer? So how can we use this approach to give an explanation for why is A not an answer? Well, if you calculate the provenance of so dominant of A is now a sentence because I plugged in a constant there. But if you calculate the provenance of dominant of A, you get a 0 polynomial because of course it's false and that you have to get a 0 polynomial. So this is not how you're going to get explanations. You're going to get explanations by calculating the provenance of the negation of dominant of A, because that one is true. And in this interpretation is going to give us a polynomial that will explain why that is true and therefore why the other one is false. So here it is. the provenance is p bar plus t. Now, remember p bar plus t, because that's the easy thing to remember. And let's look at the model again. So p bar plus t tells you that there are two alternative reasons why A is not dominant. One reason is that there's no p, because that's what, there's no edge from A to B. That's what p bar tells you. The other reason is that there is an edge from B to A. That's what t tells you. So there are two, and those are alternative reasons. Not only that, but you can also do repairs. So we just went through explanations. But you can do repairs by setting the provenance of negation of dominant of A to 0 and seeing what this means in terms of those variables. So the explanations were p bar, because, well, I just told them. But the repair is the following. In order for p bar plus t to be the 0 polynomial, both p bar and t have to be 0. Not one or the other, both. And that's the repair. And the repair is p bar equals 0, t equals 0. But wait a minute, what does that mean? What does t equals 0 mean? So remember, the repair says p bar equals 0, t equals 0. Again, I should have repeated the picture, but here it is. Setting t equals 0 means deleting the edge from B to A. Setting p bar equals 0 means inserting an edge from A to B. Now look at this picture and agree with me that if I delete the edge from B to A and I insert the edge from A to B, that makes A dominant. Now, of course, B stops being dominant, but that's not a question asked. Yes?
I thought if you didn't force me to, if I assign a literal to true, that doesn't make me assign the negative literal to false or vice versa. So how does setting p bar to 0 force an edge?
So p bar is the provenance of the fact not E of A to B.
Yeah.
So setting p bar to 0 forces that fact to be false.
Right.
So not E of A to B is false when E of A to B is true. I mean, it follows from the general theorem. I told you that what you see in those polynomials are representations, not fully, but abstract representations of those proof trees.
So I can assert the existence of an edge by either asserting the edge to exist in the edge relation, or to assert that the negative edge is false in the negative edge relation.
Yes, but remember, this is in the context of finding a repair. So what this allows you to do is figure out who the repairs are, right? But applying the repairs is a different story. Applying the repairs changes that whole provenance calculation, because now I'd have to do it again. And it will not be 0, the provenance of dominant of A. It will be something different. So this is quite general. Because you can, for example, discuss why in general a sentence fails. First of all, the sentences cover a lot of what's called integrity constraints in databases. So for instance, you can have here an integrity constraint that says at least one vertex is dominant. And okay, I'll make these slides obviously available, as usual. And you can check this yourselves. This is a lot more interesting. And what you have here is you can actually group all the repairs here. So it turns out that there's a bunch of different repairs possible here. And you can group them in an AND or tree. So when you group them in an AND or tree, the repairs are in fact expressed in a polynomial size form, although the number of repairs can be exponential, but that means exploding this tree to calculate all the possible repairs. So unfortunately, I think this is all I have time to say. There's a theorem that all the minimal repairs appear in such an AND or tree. But there's other things you can do which I didn't have time to say. So for example, once you have identified the repairs, you can actually choose between the repairs also using this provenance method to choose, for instance, a repair that's cheapest, least cost, or highest confidence. That's also possible. Okay, we extended this to list fixed point logic. And on Monday, Erich Grädel is giving a talk at Simon's that you might be interested in, because he's going to survey, starting here, a whole bunch of things that we did. You may get subjected to some stuff on model checking games that he loves. And then his student is going to talk about fixed point logics, how to do it there. So I showed you only sort of the beginning and the motivation of what we were doing. For me, this was work that actually cleared many of the concerns I had about dealing with negation. But there's a bunch of papers that are available on Archive. And the first one, we are actually right now writing, it says general version, but it's actually going to be a chapter in the Festschrift for Makowski, Johann Makowski. You know him there? Yeah. So I have to let you go. Go home. Yes, Dana.
Two questions. Trachtenberg showed that provability and finite model theory is not axiomatizable. Have you thought of provability?
This is not it. So what you have here is this kind of, not only you have model checking in finite models, because Trachtenberg's theorem is about finite models, but you have checking in finite models of a certain cardinality. That is because the set of ground values is fixed. And of course, you can always rename them, and you can consider all the models of a certain size. And that Trachtenberg's theorem does not apply to that, because it's fairly easy to see that satisfiability in all finite models of a given, if you fix the size, satisfiability in all finite models of a given size, or validity in all finite models of a given size, are decidable questions, albeit one of them is NP complete and the other one is co-NP complete.
Okay, that's a good answer. Second question. Many of my colleagues over the years have tried to apply modal logic to the law, to doing things, statements about legal questions.
Yeah.
Without any success, I would say. You have been talking about databases there.
Yeah.
But if I think, unfortunately, as I must these days, of Donald Trump, I have very little confidence in what he's saying and making his assertions.
Yes,
Do you think there might be people where the law would be interested in calculating some kind of
provenance for what they say?
Yes.
Oh, I'm sure the law would love to do that.
But can you think of some examples that would make it show that it has
So
relevance to
we can
answer the
certainly speculate, and in fact, we have extended frameworks for semiring frameworks for provenance to, let's say, fairly powerful database languages, right? But we are talking here about a narrative that is, it's not clear, it's not even necessarily logical, right? That is, it's not clear that even if we would have a way to fact check Trump's premises, that he used those premises to draw his conclusions in a manner that we can confidently say propagates that provenance. So I don't know. It's sad, but yeah. Yes.
It seems to me that like when we're thinking about provenance of statements,
Yes.
you're implicitly making a counterfactual claim. You're saying like,
Yes.
were one of these statements to be otherwise, then this would not be true.
This can be made very precise if you look at a certain kind of provenance in Boolean expressions, but a lot of it can also be captured in these dual polynomials.
But it seems like there's sort of an implicit independence assumption for all of the atomic propositions that you consider. You're assuming that you can turn some of that, you can sort of flip them independently. Where, like, for instance, I can imagine you had some situation where something was true if A were true or if B were true, but in fact A depends on B. So it's really only true if B is true.
Do you remember that theorem about triangles, that the commutation with homomorphisms?
No.
It was somewhere. If the interpretations commute with a homomorphism, then in general for any formula it commutes with the interpretation commutes with a homomorphism. So a homomorphism could be defined from the dual polynomials to themselves by mapping the x's to other x's. With that, what can you do? You can, for example, decide to label with the same indeterminate, the same token, all the information from a certain source. To make this approach work, you have to treat the negative facts in the same way. If you treat the negative facts differently, then this stops working. But assuming that everything in my graph south of Berkeley comes from a certain map, and everything north of Berkeley comes from another map, then I can certainly deal with these two sets of facts separately. And by labeling them all with the same indeterminate, I'm not making them independent anymore. That is, now in order to use that kind of provenance, I would have to interpret everything that comes from south of Berkeley in the same way. For example, give them the same confidence value. So, no, it doesn't have to be that independent. It can be, if that's what your application forces you to treat them differently. But in practice, for large models or large databases, we never do that. For large databases, for example, everything in a certain table has the same label. That's quite possible because that table was imported from, a certain scientist's database, and all we do is, we trust that person 0.8, right? And therefore I want to track that provenance together for all of them. And that I can do in a rather, if I say so myself, rather elegant way with these polynomials, just by applying a homomorphism. So this is it's a way of dealing with these things compositionally that respects abstraction and so on. Yes.
One more item. Okay. So, like for repairs, I was thinking about like how repairs could be made to respect constraints in databases. Have you thought about, like, specifically what I was thinking initially would be you have that ideal that is generated by the
PP bar. That is baked in from the beginning. So, I never calculate something that in the same monomial will have both a P and a P bar. That monomial disappears.
What I was going to ask you is maybe like if you could consider other like bigger ideals that contain like other relations in invariance that you would expect to see from.
Perhaps, but I would rather deal differently with those constraints. I would rather write a more complicated, larger first-order sentence that includes the constraints and the query ends, and I say, well, I want this to be true, but in a context in which this is true. And this is, I mean, that's actually the versatility of logic is. That's why people think this way, is because it allows us to group together these things. So I would rather do it that way, but of course we can consider other constraints in terms of the polynomials as well.
Okay, let's thank our
Kevin wants us to